first of all, we have shown that there is a one-to-one correspondence between Hochschild extensions of A by M and the second homology of A with coefficients in M, the second Hochschild homology of A with coefficients in M. And if, since during this lecture K is a field, Hochschild extension is the same thing as singular extension. So there is a one-to-one correspondence between such between equivalence classes of such exact sequences where epsilon is K algebra homomorphism such that K epsilon square is 0 and K epsilon is isomorphic to M as A by module. And the second Hochschild homology of A with coefficients in M. And then we have introduced such thing as quasi-3 algebra. And we have shown that A is quasi-3 if and only if H2 of A M is 0 for any by A by modulo M. Like this thing is obviously weaker than this thing is. So from here to here it's obvious, and from here to here it's some pullback construction, and it is equivalent to the fact that if I is an important ideal of K algebra E, then any homomorphism nu from A to E factor I can be lifted, let be bar, to nu from A to E. So there is A, there is E, there is canonical projection, here some nu bar, then there exists some nu that leaves nu bar. So in fact it's equivalent, looking at all of this, one can see that it's equivalent that any surjective algebra homomorphism E to A with nilpotent kernel, so such that K epsilon and the nth power is 0 for some M splits as a homomorphism of K algebras. Well, so this is what we need to prove so-called Vandermarson theorem. But to formulate it and so on, we will need some portion of ring theory. Non-commutative ring theory. Well, this portion is about Jackson ideal. I don't know. Do you know what is Jackson ideal or not? Well, probably we can omit something. So to define and formulate what we need about it. If you know the proof, we will not prove, okay? Because it's not part of homological algebra. Let A be okay algebra. In fact, of course, Jackson ideal can be defined for any ring, but we now study only finite dimensional algebras of a field, so let be a finite dimensional algebra our field K. So it's called not Jacobson ideal, of course, Jacobson radical of A is the set JA, it will be denoted, which is the set of such A in A, that be R in A, that 1 plus or minus, I don't remember. Yeah, it's not important, of course, but let be minus T R S is invertible. So I send A star is invertible elements for any R T and S and R in A. Well, there are different definitions of Jacobson ideal, and of course all of them are equivalent. This one is symmetric, and from the definition it's clear that JA is a two-sided ideal. So lemma, which formulates other definitions, is the following. That JA can be defined in 5 different ways. Yes. So it is intersection of I for all I maximal left ideal of A. It is the same as intersection of I, where I sorry. Is maximal. All right. Ideal of A. It is the same thing as the set of such R from A that 1 minus RS is invertible for any S from A, and of course the same thing as the set of such R from A that 1 minus TR is invertible for any T from A. Well, do I need to prove it or not? No?
No, it was part of our basic algebra course.
Oh, okay, I didn't know. Well, so who don't know, it's exercise from basic algebra course. So what else do we need about Jacobson ideal? Nakayama lemma. Do you know what's this or not? Do you know that Jacobson ideal of finite dimensional algebra is nilpotent or not? No? Yes? How have you proved this?
It was the definition, and we proved.
What?
And we proved it was the definition, like maximum nilpotent ideal.
And you have proved that all of this. I think at some moment you had to prove Nakayama lemma. So I will formulate Nakayama lemma for you know what's this, but probably you have proved it too. If M is a finitely generated module over A such that M is equal to M ut A, then M is 0.
It wasn't part of the basic course, it was some commutative algebra, but it's like...
Okay, so, well, it's not very difficult. This lemma would take more time. So proof, suppose that M is generated by, so M is finitely generated, so we can choose some set of generators of M. Let us choose a set of generators of M with minimal number of generators. So choose. So suppose that M is equal to MJA. Let us choose so x1, so on xt, xm, generating M as a module, of course, finally generate the same module, of course. Module with minimal M. Well, so in this case, we know that xm, for example, lies in mja, and we know that it is what it lies in the sum xi a ja, which is sum xi ja. This means that xm is equal to the sum for I from 1 to m xi, let it be, how to call it, xi, okay, ri, where ri lies in the Jacobson ideal. Then you have xm 1 minus ri is equal to the sum for I from 1 to m xi ri to m minus 1. And since Rm is from Jacobson ideal, this guy is invertible, so we have xm is equal to the sum I from 1 to m minus 1 xi ri 1 minus rm minus 1, and hence x1 xm minus 1 generate m. So m is not minimum, and we have a contradiction. In contradiction to what? Because we almost don't assume anything. We assume that m is mja, and we assume that m small is more equal to 1 to choose xm, yes? So this contradicts to the fact that to m more equal than 1. So m is 0, and hence the module is 0, and we have done. We are done. So from this it follows that wait a minute. How have you defined the Jacobson ideal?
Like maximum important ideal whose factor doesn't contain non-zero important ideals.
And for what? For nearing?
For any group representation theory.
But it was definition for what type of ring?
For Artinian ring. For any Artinian ring.
It's strange.
I remember Well, Artinian is some intersection of all nilpotent elements. Nilpotent ideals.
Well, okay, for Artinian rings, yes, probably. Because as I know, this definition can be applied to any ring, and for non-Artinian ring, I think that it doesn't have to be nilpotent. Something like this. So corollary is that JA is nilpotent. In our case of finite dimensional algebra of a field, yes. And the proof now is simple. So we simply consider the intersection. Suppose that the intersection of JA in the kth power for k more equal to 1 is not 0. I don't know where. Well, we don't need to suppose anything. We simply consider it. We simply note that if you take the intersection of JA in the kth power for k more equal than 1 and multiply it by JA, we get an intersection, the intersection for k more equal than 2 J in the kth power, which is the same thing as intersection for k more equal to 1 J in the kth power, and hence the intersection J in the kth power is 0. And since we have a finite dimensional algebra, our field, this means that there is some m such that J in the nth power is 0, because this ideals is a sequence of descending ideals, yes, and so it stops at some moment. It stabilizes some moment, and where it stabilizes, we get to the intersection. But since the intersection is 0, it stabilizes at 0. And for Artinian algebra, of course, the same thing is. Okay, so J is nilpotent. And now a fact about Jacobson radical. Is that if A is finite dimensional K algebra, then A factor JA is a semi-simple algebra. Have you proved this or not? No. So, what is semi-simple algebra? Do you know? Definition. Well, so what I recall you the definition that algebra B is semi-simple if B is a semi-simple module over itself, and semi-simple module is semi-simple module is a module such that any its submodule is a direct summand, and for finitely generated modules, our finite dimensional algebra or finite dimensional algebra, it is equivalent to be a direct sum of simple modules and simple module, you know what's this? It is a module that has only two submodules itself and zero submodule. Well, we will not prove this, but to be semi-simple on the right and on the left is the same thing because of for finite dimensional algebras. It is the same thing because of classification theorem of Wardenberg, yes, that says that any semi-simple finite dimensional algebras are exactly algebras of the form sum of mi of gi, where so mmi is the ring of matrices mi times mi, where gi is a finite dimensional skew field over K. So everything follows from this. It follows that semi-simple on the left and the right is the same thing, and even we know that what algebra is semi-simple, but we will not prove it. Have we proved it? Of course. But we can't prove it at our course. It is quite difficult theorem and outside of homological algebra. There's some theorem which is very near to basic course, but not there. So to prove that a factor JA, well, everything that we will prove will not require this, but in fact, to make sense, it requires this. Well, we will prove something, and all our proofs will not be based on this, but to apply these results, of course, one has to have this, something like this. For this result, have some value. So the proof of the theorem is quite simple. A is finite dimensional algebra that I1, I2, and so on be all maximal. Right ideals of A. Then we can start to intersect them. So that I1, then I1 intersect I2, and so on. And of course, at some point, we get the intersection of all ideals. So at some point, like 1, so on, I M equals JA, yes. And then we have A factor JA is isomorphic to direct sum. So it is, of course, A factor intersection of I for I from 1 to m. It is isomorphic to the direct sum of A factor I for I from 1 to m. Why it's so? It is something like Chinese remind theorem, but of course nobody formulated in such way. Chinese reminder theorem is for commutative ring usually, but it's something like direct generalization to non-commutative rings. Yes, you simply here A plus JA, you put in correspondence A plus I1, so on, A plus IM, and it's easy to see that II plus IJ is equal to A for I not equal to J, yes. And so exactly how it is proved in Chinese remainder theory, one can prove that this map is isomorphism. So now can formulate the numeral maps Maltsev theorem. We will formulate it in a little wrong way, so let us call it Weddenborn. Part. In fact, what I will formulate is called Weddenborn principal theorem, because and Weddenborn-Maltsev theorem is Weddenborn principal theorem plus something, but we will formulate it as two theorems. If a factor JA is a projective a factor JA E module, then A is isomorphic to the semi-direct product JA JA for some a factor JA by module structure on JA the proof is nothing, of course, yes, because because if A is A factor J is A sorry, 2 minutes. Yes. Well, if A factor JA is a factor JE projective module, then HH2 of A factor JA M, which is X to A factor JA E A factor JA M is 0, since this module is projective for any A factor JA E module M, then A factor JA is quasi 3, and hence the sequence, hence the surjective epi, the surjective homomorphism A factor JA splits since JA is nilpotent. And so we are done because of course this gives such an isomorphism. You simply take JA and the image of A factor J under the splitting homomorphism. Yes. Well, so it is a like big part of the structure of theory of finite dimensional algebras of a field. At first view, it's not clear why, because there are some like assumptions, and it's not clear why we assume this. Is it always satisfied? How often it's satisfied? But this condition that A factor J is projective over as a bimodule over itself is quite natural, and we will study it at seminar, in fact. But for example, for algebra over algebraically closed field, it is always so. So corollary. If K is a K algebra, K is algebraically closed, then A is isomorphic to the semi-direct product of Jackson radical and the factor. And we will not prove this like in full sense of this, because in any case the proof requires the Wadenberg classification theorem. A factor JA is isomorphic to mi of di. And since K is algebraically closed, di is equal to K, of course. You know this, that if K is algebraically closed, there are no finite dimensional skew field over K except itself. Then A factor JA is isomorphic to direct sum mi of K, and corollary follows from the fact that m of K is projective over m of K E for any m let us call this exercise. In fact, we will prove this at seminars. So, like, this corollary is to illustrate that this theory works, and in some like big enough quantity of cases, but like we don't pretend that we have proved this corollary. While the most difficult part, of course, is the classification. We have not proved, so because of this, I will not pretend to give any proof. In fact, this theorem works in a bigger number of cases. It works, in fact, for any perfect field, but for perfect field it's a little more complicated to give even a sketch of proof. And but at our seminars we'll show that for perfect field, a factor ja is a projective a factor ja bimodule. So what we have proved is called variable principal theorem, and Maltsev part of this theorem is another thing that we haven't formulated. Maltsev part is related to the question about uniqueness of this semi-direct product. If you have algebra A and you have the isomorphism, A is isomorphic to n semi-direct product S, yes, where n is nilpotent, and S is semi-simple, then in fact it's easy to see that JA is isomorphic to n, is equal to n. Yes, and S is isomorphic to a factor JA. So this isomorphism is the same thing as A is isomorphic to a factor JA. JA. A factor JA. Yes. So, but what can be different here? What can be different?
Model structure.
Model structure, yes, of this and this. And Maltsev was worried about how this models, how to describe all model structures that can arise. Yes. So if you have A, yes, and we want to look how many these presentations A have, yes, then we easily see that JA is uniquely determined, yes, because it's Jacobson radical and it is something which is determined by A. But A factor J as a subalgebra is not determined. It's determined only as an algebra. And so the Maltsev part describes all subalgebras that can appear as A factor J in some sense. So then Maltsev theorem, it's Maltsev part. Suppose that we have two subalgebras semi-simple, of course. S1 and S2. The conditions are the same. Etc. That A is a finite dimensional algebra over field K, and that A factor J is a projective A factor J E module. Like two subalgebras inducing isomorphisms JA S1 is isomorph to A to JA S2. Then there exists R in JA such that S2 is equal to 1 plus R, S2, 1 plus R plus 1. So any two subalgebras inducing such isomorphism are conjugated by some element of this form. And so you can see that the modular structure, bimodular structure on JA is determined modulo the conjugation of element of this form too. So let us prove it. So let us prove by induction on M that there exists R from JA such that 1 plus R x 1 plus R minus 1 belongs to S2 for any x from S1 belongs to S2 plus JA in the nth power. And let's call it Rm. Yes. Then, since there exists m such that j in the nth power is 0, we can take Rm for this m, and we will get the required, this one, of course, the required condition. Yes. Because everything is finite dimensional, it's clear that the conjugation is bijection. If we take some set and the image of this set then is bijection with this set and its image. So S1 and S2 have the same dimension, so we will have that S2 is equal to 1 plus R, S1, 1 plus R minus 1. It is enough since JA then power is 0 for some n. So let us start with the base. Yes. So we have base case n equals 1. So we have two sections of the, we have the projection A to A factor JA, and we have two sections. From A factor JA to A, sigma 1 and sigma 2, where the image of sigma 1 is S1, image of sigma 2 is S2. Yes. So let's now consider well, for any x, we can consider sigma 1 of x, yes, and sigma 2 of x. And if we apply rho, we will get 0, of course. So sigma 1 of x is equal to sigma 2 of x plus gamma of x for some gamma from A factor JA to JA. Yes. So, sorry. So from this, it follows that sigma 1 minus 2 of x lies in JA. So this, yes. Because JA is the kernel of rho. Yes. So we get some gamma such that this equality is satisfied. Sorry. Wait a minute. first of all we have to understand something. Yes. So we know that sigma 1 and sigma 2 are homomorphisms, yes? So we have sigma 1 of x, sigma 2 of x is equal to sigma 1 of y, yes, is equal to sigma 1 of xy. So on one hand it's equal to sigma 2 of x plus gamma of x, sigma 2 of y plus gamma of y, and on the other hand it's equal to sigma 2 of xy plus gamma of xy. Yes. Then what do we see? We see that this product will cancel with this, of course. So we will get the equality, like sigma 2 of x gamma of y minus gamma of xy plus gamma of x sigma 2 of y plus gamma of x gamma of y is equal to 0. Yes. Well, so now let us consider gamma bar, yes, from a factor ja to ja factor ja square, which is simply gamma and then the canonical projection. Yes, then for this gamma bar, we know that first of all, this guy is a factor ja bimodule via sigma 2. Via sigma 2 means that exactly for like a from ja factor ja square and for like x in a factor ja, the multiplication is and x and y. The multiplication x a bar y is exactly sigma 2 of x a sigma 2 of y bar. Yes. And then this equality can be rewritten as x gamma of y minus gamma of xy plus gamma of xy is 0 because this guy is 0 here, yes. Because we take ja factor ja square. Sorry, bar. Well, but we know that a factor ja is a projective bimodule, so gamma bar is gamma bar determines some place in HH1 of a factor ja factor ja square, which is 0. Yes. So it determines 0 class. So we have gamma bar of x is equal to of x is equal to x r1 minus r1 x bar for some r1 from J. And bar here is the class in J factor J square, of course. Yes. What does this mean? This means that sigma 1 of x is equal to sigma 2 of x plus gamma of x, which is let us write in this way. It's the same thing, yes. So plus r1 x minus x r1 plus gamma 2 of x, where this element now is in J square. Yes. So and we have now sorry, what's one? So it's sigma 2 of x, yes. Here sigma 2 of x. Well, I have mixed or something, so let it be in this way, yes, because we are proving this. We simply interchange here S1 and S2. Well, so what's this? We now can take 1 plus R1 sigma 2 of x 1 plus r1 minus 1. Yes. What is 1 plus r1 minus 1? It is, of course, 1 minus r1 plus r1 square minus r1 cube plus so on. Yes. And what's the difference? The difference is gamma 2 of x, which is in J square. Then also plus r1 sigma 2 of x r1, yes, which is in J square. And what also, and this part, yes, which is minus 1 plus r1 sigma 2 of x, and here like r1 square minus r1 cube plus so on, which is J square. Is in J square because this guy is in J square. Like 1 plus r1 the inverse of 1 plus r1 is 1 minus r1 modulo J square. This is what I want to say. So we get our equality that if we take 1 plus r1, then this element differs from this element by some element of J square. Base case is proved. Well, the induction step, of course, very similar to the base case. So if we have proved that like sigma 1 of x is equal to 1 plus Rm sigma 2 of x 1 minus Rm 1 plus Rm minus 1 plus something from Ja in the nth power, then we can replace sigma 2 of x by sigma 2 prime of x, which is equal to 1 plus Rm sigma 2 of x 1 plus Rm minus 1, and assume that sigma 1 of x is equal to sigma 2 of x plus gamma of x for some gamma from a factor Ja to Ja in the nth power. So now we again write this equality. Yes. What equality? This equality.
Excuse me. That Rm inverse is with inside of.
Sorry. Now we can write this equality. Yes. And we will get again this equality, and then we simply change here. So we have sigma 2 of x, gamma of y, minus gamma of xy plus gamma of x, sigma 2 of y plus gamma of x, gamma of y equals 0. And then we consider again gamma bar from a factor Ja to Ja in the nth power factor Ja in the n plus 1th power. And for gamma bar we have, and here we have again the bimodule structure. We are sigma 2 factor Ja bimodule. We are sigma 2, and we again will have x gamma bar of y minus gamma bar of xy plus gamma bar of x y is 0. So we again have that gamma bar of x is equal to r m plus 1 x minus x r m plus 1. In fact, for some r m plus 1 from Ja in the nth power. And then, if we do the same thing, we will get that sigma 1 of x is equal to 1 plus Rm plus 1, sigma 2 of x, 1 plus Rm plus 1 minus 1 plus gamma m plus 1 of x, well, this guy is in JA m plus 1 now. Yes. Well, so in fact we'll put here sigma 2 prime to not have, if it confuses somebody. So in fact we have, it is 1 plus r plus 1, 1 plus rm, sigma 2 of x one plus rm, 1 plus rm plus 1, sorry, minus 1, and this guy is 1 plus rm plus rm plus 1 plus rm plus 1, and in fact this guy is what we have to take in the role of Rm plus 1, of course. And plus something from JA in the m plus 1 power. But in any case, we have made the induction step, so we are done. So we have shown that any finite dimensional algebra is a semi-direct product of some nilpotent part and some semi-simple part, and this decomposition is unique modular conjugation by an element of some special way, some special form. So I think we have finished our lecture course. Do you have some questions?